Hello, and welcome back to Physics Rich. Guys, we are doing lecture 3, part 2 of fluid statics. So, in this lecture, we will try to complete the concept of Archimedes Principle and we will pick right off where we left the previous lecture. If you have not seen the previous lecture, please go back and take a look at it, and only then you'll be able to understand what we are doing in this lecture. So let's begin with the same problem that I left you with, and this was the question that we were doing. So here I had explained to you that at point A and B there is the same pressure, and at point C there is pressure due to mg and due to pseudo force both, as we can see that this is a container which is accelerating in this direction, and that's the reason why liquid has been accumulated onto the left side. But always remember that the pressure is not due to individually G or individually the pseudo force, it's due to the net force. All right, must remember that pressure is due to the net force. Now let's go to this very nice question. It's a very important question, guys. We will analyze what is happening over here. In such situations, most likely he will ask you the height difference. He'll ask you to find the height difference. Okay, so how shall we go about it? So in this question, the first thing we should notice is that, well, this point, okay, let's call this point as M. Why am I calling it M? M stands for like midpoint. It's not the midpoint, but it's like on the axis. That's why I'm calling it M. Okay, let's call this point X and let's call this point Y. This is the free surface and this is also the free surface. So at free surface, the pressure is P naught. All right. So what you can understand over here, guys, is that if this is, let's say, H1 and this is, let's say, H2, then pressure at Y should be equal to P naught plus rho G H2, and pressure at X should be P naught plus rho G H1. Okay. Now, one very important thing, guys. What is the pressure at the point M? We will assume that the pressure at point M should be equal to 0. All right. We will assume that because the fluid is being pushed, I mean, to this point, the left of it, the fluid is being pushed towards the left, and to the right side, the fluid is being pushed towards the right. Now, why is this happening? This is happening because of centrifugal forces. All right. So, what can you say about the pressure at the point Y if we go in this direction along this part of the tube? So, we can simply say that the pressure at the point Y should be equal to the pressure at the point M plus half rho omega square 2L square. All right. Pressure at point X is pressure at point M plus half rho omega square L square. Now you see, guys, that if I find the difference of pressures between Y and X, I can do it using two of these equations. Okay, I can use these orange equations and I can subtract them, and I can get that the pressure of Y minus pressure of X comes out to be equal to rho G H2 minus H1, and this C H2 minus H1 is the height difference that we are trying to calculate. That is Py minus Px, the difference of these two. Pm is going to get cut anyway. So these two, all right. So this will be half rho omega square. Now see, this is 4L square, this is L square. This is going to be 3L square, correct? From here, we can find out H2 minus H1 simply comes out to be, see, the rho gets cancelled. So this is omega square times 3, and this is well, L square upon G. Okay, fair enough. All right, let's move on to the next question. Also, one very important thing, guys, over here, you can understand that this height difference, this H2 minus H1, which is 3 by 2, I forgot a 2 over here. So this is a 3 omega square L square by 2G. This height difference, okay, is over here, this is the height difference. You see, this is the height difference. This is the height difference. Okay. So if it has gone down by x, this side has moved up by x. So he can ask you, like, by what height does this thing rise? Okay. Or by what height does this original level fall down? So you take this, divide it into 2, and that's your answer, which is just 3 by 4 omega square L square upon G. Okay. Let's try to do this quite easy question that came in JEE 2025 mains in the January shift. So what is happening here? There is this rod which has mass of 2m. I mean, there's a fluid inside of it which has mass 2m, and it's going around in a circle. Okay, it's going around with omega. And he's saying that the angular velocity is square root of f upon alpha m, where the length is 1 meter. Okay, so what can you do? You can simply say that this force, all right, this force is responsible for making it rotate. And what is the pressure over here? The pressure is just simply going to be half rho omega square L square. Okay, it's just simply going to be half rho omega square L square. Now you can take this force, which is going to be like the pressure multiplied by area. Pressure is half rho omega square L square. Force will be this multiplied by the area. Okay, this force is going to give you the centripetal acceleration. So you can write it like this: half rho omega square L square times A. Okay, that becomes equals to this 2m omega square L by 2. In fact, we actually don't even need this part. We don't need this part, right? There's no need for this pressure. In fact, there's no need for this at all. So we can just simply solve it using this. Okay, this part. Because see, force is the one that is giving us the centripetal acceleration. Now, what is the centripetal acceleration? Mass times omega square times the distance of the center of mass from the axis. So 2m omega square L by 2. L is just simply 1. 2 gets cancelled. A is anyway getting cancelled. So omega square simply comes out to be equal to F by ml. F by ml. And L is given to you as 1. So omega is the square root of F by m. That's why the answer to this is alpha equals to 1. Very simple, very easy, very scoring question. Okay. Let's take another look at this problem. You can pause the video and you can read for yourself, and I'll solve it in a moment. There's a long cylinder which is half filled with a liquid, and the vessel is rotated about its own vertical axis. So there's a long cylinder, kind of like this one. Okay, there's a long cylinder, and then it's filled with liquid, and then you rotate it, and liquid is seen to be rising along the wall. Let's make the liquid in blue color. It's kind of like this. Okay, and radius of the vessel is given to you as 5. This is 5 centimeter. Okay, and rotational speed is 2 rotations per second. So 2 rotations per second is the same thing as 2 revolutions per second, which is the same thing as 4 pi radians per second. Now you can simply apply the formula y equals to omega square r square upon 2g, which we found out in the previous video, in the previous slides. So you can just put the value of omega, put the value of r is 5 centimeter, 5 into 10 power minus 2, and then divide by 2 times of g. Make sure that you put pi square as 10, and then you will be able to solve it, and you will get the answer as 2 centimeters. Okay, so what is the answer? It's 2 centimeters, right? Easy, easy peasy. Moving on, let's go. Now here we have a JEE advanced question. Okay, it's a JEE advanced question, guys. This came in 2020, and this problem was actually considered an easy problem. And just take a look and read it by yourself. This problem can easily be solved based on the other problems and the ideas that we have discussed in the past. So let's take a quick reading, or you can pause the video and read it for yourself. So we have an open-ended U-tube of uniform cross-sectional area, and it has water in it. The initial level is 0.29 meter. So I have made this U-tube over here. this initial level 0.29. Okay, and then you start pouring kerosene from this side. You start pouring kerosene from this side, and how much kerosene do you pour? You pour 0.1 meter of length of kerosene. Okay, and the density of kerosene is also given to you. Okay, now he says that what is the ratio of H1 by H2 of the heights of the liquid in the two arms? So what do you do, guys? Again, very simple. You can just check that, you can just see that by pouring kerosene, the liquid will lift up. It will lift up by a certain amount. Okay. So this height will become 29. It was initially 29. Okay. This should become 29 plus x. Okay. This should become 29 plus x. We are assuming how much it has lifted up. And this will go down and it will become 29 minus x. Okay. It should become 29 minus x, because earlier it was 29.29 meter is just 29 centimeters. Okay. So this is 29 centimeters plus x. This is 29 centimeters minus x. Okay. Now, what can you do now? What else can be done? So what is the difference between these two? What is the difference between these two? The difference between these two will be 2x. So very simply, guys, you can just say that the pressure will be same at this level. Okay. So density of kerosene times rho GH, right? Pressure is rho GH. Rho of kerosene, G, and height of kerosene is 0.1 meter. 0.1 meter. That is equal to density of water times G. And by what is the difference now? The difference is actually 2x. 2x. Okay. So you can find out that G cancels. Okay. And this x comes out as density of kerosene times 0.1 upon density of water times 2. Okay. Density of kerosene is 800. Density of water is 1000. So this is going to be 0.8 times 0.1 by 2. Okay. How much is this? This is actually 0.04. This is 0.04. I hope that is clear. So what it means is that this height H2 is basically 29 centimeters plus 4 centimeters. By the way, this has been found out in meters. So this is 4 centimeters. Okay. So this must be 29 plus 4. 29 plus 4 is how much? 33. And this is 29 minus 4. 29 minus 4 is how much? It's 25. Okay, so this is 25. So this is 25. All right. But you see there is a 0.1 meter on top of it. So 25 plus 10. So we are supposed to do 29 minus x plus 10 plus 10, and that is 35. So what is H1 by H2? H1 is 35 and H2 is 33. So 35 by 33 is our answer. The question is actually so simple that if this question came in advance, you would start to think that something's wrong with me. Maybe I am not getting it right, because how can I get this so easily? But guys, this is one thing that advanced sometimes tests. It will throw you a slower ball, right? In cricket, you play cricket, right? A simple slow ball is thrown, you start feeling like, you know what, I'm just gonna hit it out for a 6. But then all of a sudden you sometimes mistime it, and then you probably get bowled out, or you get stumping out, or you might even edge it and get a dismissal. Simple thing sometimes becomes difficult. So that's what JEE Advanced sometimes does. They give you some easy questions in the middle of tough questions, just to see how composed you are in your mind. So JEE is not just an exam for the testing your intelligence. It is also an exam for testing your composure. All right. So it is important to maintain your composure. So guys, we are now talking about Archimedes principle, and Speaking of composure, this actually is a story of composure, right? Let me tell you how. So there was this place in Italy. It was called Syracuse, all right? And there was a king over there, and he ordered a crown for himself made of solid gold, and he gave a certain amount of gold to the goldsmith to make a crown. Now when the crown was handed over to the king thought that perhaps the goldsmith has done some forgery in it, and even though it looks like an original crown, it's not an original crown. So he wanted to find out, without destroying or melting the crown, how can we find out if this has pure gold in it? And he gave this problem to a very old scientist in Syracuse. His name was Archimedes. And the best thing about Archimedes was that he was known for being very calm and composed, and because he was lost in his thoughts, he used to remain lost in his ideas. And that's what I think is a very important nature of all science students. I think that these days science students, they just want to somehow solve problems. That's not how it is done, guys. A lot of times you will find good information dawn upon you because you have spent enough time thinking about it. So Archimedes was thinking about the problem, and well, he was taking a bath at that time, and this problem is actually solved using fluid statics. Well, to find out the purity of the crown, the gold used in crown, you need fluid statics. How cool is that? So Archimedes came up with this, and he was calm and composed, but he forgot that he was taking a bath, and then he ran out in the streets and he started yelling "Eureka!" And after a very long time, he realized that he was not wearing any clothes. So yeah, guys, life is a test of composure, not only your knowledge. Okay, so let's learn about what exactly is it that Archimedes found out. So Archimedes' principle says that upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially, is equal to the weight of the fluid that the body displaces. Now, just by reading the statement, you will not really get the idea behind it, but let me explain to you how this works. So you see that there is this vessel, and there is a golden bar on top of it. What is the force acting on this golden bar? This is mg, only the weight acts. And as this falls down, okay, what happens is that it makes space for itself. And in order to make space for itself, it has to push this fluid out. This amount of fluid is pushed out. Okay. Now, this amount of fluid that is pushed out, we have collected it over here. And when this goes inside the fluid, we realize that not only the gold bar experiences an mg force downwards, but also a buoyant force upwards. So the net downward force after complete submersion is mg minus fb. Now Archimedes' principle says that there is an upward buoyant force. So what's the meaning of buoyant force? Buoyant force is basically a force that liquid exerts or a fluid exerts. It's not necessarily liquid, but even gases can exert this force in the upward direction against the gravity. Okay. So wherever is the G effective, so this buoyant force is exerted in the direction opposite to that. So this, whatever is the weight of this displaced fluid, that much force will be acting in the upward direction. Now you must be confused, but sir, isn't that the weight always acts in the downward direction? And the answer is yes, my dear students, the weight always acts in the downward direction. But we are talking about the weight of this displaced fluid, this fluid which is moved out. Okay, the weight of this fluid is acting on this fluid in downward direction only. But the magnitude of this acts in the upward direction, and that force on this gold bar is called the buoyant force. All right. Now, we will try to understand this even better. So, the upward thrust, upthrust or upward thrust, upthrust or upward thrust, these are the same words, all right, same meanings. This is called the buoyant force, all right, this is called the buoyant force, and it is dependent on how much fluid, how much is the weight of the fluid that is moved or that is displaced. Now, this fluid, as it has been moved out, what it tries to do is that it tries to come back into its original position. It's kind of like saying that when you are entering into a train, okay, and then you ask a small child to get up, and that's the reason is that you want to sit over there, then the child will stand right in front of you and he will keep waiting for you to move away so that he can sit back. All right, such an uncomfortable situation. Okay, so this is exactly what this water is trying to do. If you put any object inside fluid, the fluid which was present over there would move up and it will wait that, you know what, I want to get back into that original position. And that is why it applies a force equal to its own weight, and that force is what is called the upthrust. Okay. So this moved up fluid is obviously equal in volume. Okay, it's equal in volume. How much ever you will submerge, like for example this sphere, it is now submerged, like half of it is submerged. So how much is the buoyant force? So first of all, if you submerged only half of it, so well, the volume has to be equal. No, like how much has this been submerged? The half of this sphere has been submerged. So only this part will be displaced. Okay. So what will be the buoyant force? The buoyant force will be the weight of this part, but in the upward direction. And I have written the weight of this part over here. So weight of the hemisphere, like hemisphere of the liquid, will be the volume of the liquid multiplied by the density of water. Okay. And if you submerge it completely, then it will be the total volume of the sphere multiplied by the density of the water. Okay. So the buoyant force always acts at the geometrical center of the submerged part. You see that this part is now, this part was earlier water. Okay. Earlier there was water over here. But now what do we have? We have the object. So it says that because the buoyant force is acting due to the presence of gravity, due to the presence of pressure difference. So because in all this region, there's uniform gravity. That's why the buoyant force also has a center of application. And that force is acting at the center of this region which has been displaced. Okay. Now we design ships in such a manner that the buoyant force equals to the weight of the ship. But how do we ensure stability? Is it possible that because this ship tilts over this side, perhaps the buoyant force increases so much, like you can see, like as this ship tilts, all right, this ship tilts. So now greater part of the ship is now submerged. Okay. So there is more buoyant force now because there is more of the liquid that is being displaced. So is it possible that this buoyant force increases and, you know, causes the ship to capsize? Capsize means like, you know, to tilt over. But no, that's not going to happen because we design ships in such a way that this mg force and this buoyant force, they cause a torque in such a way that this ship comes back to in stable equilibrium. Okay, so that is how these ships are designed. So we design them in such a way that the center of mass of the ship is like kept very low. And yeah, like I was saying that buoyancy is present in both gases as well as liquids. Okay, and the magnitude of upthrust is given by this formula. Please note this down in your notebooks. Buoyant force is equals to the density of the fluid times the displaced volume times G. Now, this, you see this pirate ship, okay, this pirate ship, I can't stop myself from the music, epic music, you know, Pirates of the Caribbean. So the ship is submerged, all right. How much ever the volume is submerged, that much volume will be displaced, all right. And this pirate ship will experience an upthrust due to only its submerged portion. Please do not be confused. It does not experience force equal to its own weight all the time. It can be displacing perhaps sometimes even more water, more weight of water than its own weight, like in the case of tilting and all that. Okay, in that case, it can experience a different kind of buoyant force, but it stays stable because the buoyant force is more or less equal to the weight that it has. Okay, and how much is that buoyant force? It is whatever the submerged volume of the ship is times the density of water times gravity. Okay. Now, this upthrust or is this buoyant force is again due to molecular collisions only. Okay, fluids do not apply any other force than molecular than due to molecular collisions. There's another force called surface tension that they apply, but we have not discussed it yet, so we'll not go into that, but I will teach you that in the upcoming videos. But all forces on this ship or any other container or any kind of force that liquid applies is only due to molecular collisions. Okay, so now we are assuming that there is a certain cylinder over here. Again, this cylinder is a hypothetical cylinder. It's not a real cylinder. It is just a boundary. It's just this part is just imaginary, and we are analyzing what happens in this imaginary part. Okay, so the whole thing is liquid, and this cylinder is also liquid. Is this stable? Is this an equilibrium? Yes, that's an equilibrium. If I replace it with another cylinder, if I replace it with, let's say, this cylinder made of gold, will it be in equilibrium? No, because perhaps the weight of this golden cylinder will be more, so it will sink down. But we can still find out whatever will be the buoyant force by calculating the weight of this part and the force due to pressure difference. So you see, guys, that if we try to find the force on the upper portion, that will be P1A, this much. On the lower portion, it will be P2A, which will be this much. And the net force must be equal to 0. So the weight which is acting downward plus this downward force due to pressure on the upward surface should be equal to the upward force, which is this much, due to the pressure at this point, pressure at point A. So if we calculate what is this weight will come out to be equal to rho g delta h A. All right, and you see this delta PA, this itself is the net buoyant force, net upward buoyant force. And we have proved that it is equal to the weight of the fluid column which has been displaced. All right, so remember, guys, rho Vg, it's always the buoyant force. Now, the problem that I have seen my students undergo is that they forget which volume to take. They think that maybe we can take the volume of the whole object, but then, guys, remember the pirate ship. The pirate ship does not experience buoyant force because of its large volume. It experiences buoyant force because of the volume that has submerged, which has been submerged inside. Okay, it experiences weight because of how much volume it displaces. Buoyant force, sorry, it experiences buoyant force because of how much volume it displaces. Okay, so now, like I said, that this thrust is due to pressure difference, which is due to molecular collisions. And the upthrust itself is the reaction force to the force applied by the body on the fluid. Now, students sometimes start to think that there is a buoyant force, there must be a normal reaction also. And the answer is no, guys, there is no such normal reaction. Buoyant force is the only reaction force that the fluid provides to this submerged body. Okay, so the only two forces that are acting on this are buoyant force and weight. What is flotation? Now, flotation, guys, is a very interesting idea. Now, we are trying to investigate as to why anything floats. I would like you guys to read this slide at least once. So we have a body which is resting on the surface of the liquid, and that is what we call flotation, as in it is not sinking. Okay, now you see that this sort of not sinking is only possible if the weight of the body is balanced by the upthrust. Okay, if the upthrust due to the submerged part is balancing the weight of this body, if this upthrust cannot balance the weight of the body, that's when the body will sink. See what is happening over here. So weight of the object is equal to the weight of the displaced fluid. So what can you write about the weight of the object? Mass of the object times gravity g. Mass of the displaced fluid times g is the weight of the displaced fluid. And if we equate them, the g cancels. So their masses should be equal. Mass of what? Mass of the object and mass of the displaced fluid. All right. Even for a pirate ship, even for a cruise ship, anything that sails, even for INS Vikrant, the weight of INS Vikrant has to be equal to the weight of the water that it is displacing. Okay. So what's happening here? Mass of the object is rho v, where v is the volume of the object. Rho is the density of the object. Mass of the displaced fluid is density of water times submerged volume. So I've taken that to be sigma Vs. Density of water I've taken to be sigma. Vs is the submerged volume. So that's why rho v should be equal to sigma Vs. Now you see guys, by that logic I get Vs by V equals to rho by sigma. Now, if there is no sinking, if sinking is not happening, then the submerged volume is lesser than the total volume, correct? Which means that this must be less than 1. Well, obviously, the numerator is lesser than the denominator, so this fraction is less than 1, which means that if the fluid density is more than the object density, then the object naturally floats. Okay, so if you want an object to float, you must ensure that its density is lesser than the density of the fluid that you are throwing it in. Fun fact, take a metal coin, throw it in water, you will see that it sinks. But take a metal coin, throw it on mercury, you will see that it floats. Why is it that way? Because the density of mercury is very high, correct? That's the reason why even coins float on mercury. Human bodies, why do we float? We float when we try. We don't float just like that. You throw a person who can't swim in water, they will obviously sink. Okay, please don't do that. It's just very cruel. Okay, don't do that. But yeah, if somebody who knows how to swim, like I know, if I jump into a swimming pool, I can't talk about, like, I can't tell about rivers and all. Those are very dangerous things. I don't want to swim in a river because it has flow, and then the fluid dynamics comes in, and so much happens. Bernoulli's equation, viscosity, yada yada stuff happens. No, I don't want to. I don't want to deal with all of that. But I'm happy swimming in a swimming pool where the fluid is static, because we're studying fluid statics. So if I jump into the pool, I will try to swim. Okay, and how will I try? I will just flap my hands around and I will push the water down, and it will give me a certain more reaction force. Okay, if it gives me generates a bit more reaction force, then I will be able to stay afloat. Can we do that in air, however? No, we can't do that in air. We cannot do that in air. So if at all, a human wants to fly, the span of wings that they will require is 10 meters. Okay, I will need a 5-meter wing on this side and a 5-meter wing on that side, which is again 10 meters is what, like 3-story building. Okay, very huge wings. And in that case also, my arms will not have that kind of power to flap my wings and then just try to fly. So it's impossible for humans to fly. Okay, if you figure out a way to find if you figure out a way to fly, do let me know. I would be highly interested. Okay, it'll be fun to fly, but please make sure that your design is perfect. So what do we have here, guys? We have an object floating on water. We see that this is the submerged portion. This is the total volume. So Vs upon V is rho by sigma. Now you see that what is rho by sigma? See, rho by sigma is basically the relative density. Okay, right? Rho by sigma is the relative density, where sigma is the density of the fluid. All right. So if we take this to be the density of water, then what we are talking about? We are talking about the specific gravity, Sg. Okay. So if the Sg of ice is 0.9, okay, this ratio is 0.9, which means the submerged volume upon the total volume is also going to be 0.9. You know what it means? It is 90% inside water. Remember something? Icebergs Icebergs are 90% in water, 10% outside. Do you know why? It's because the SG, the specific gravity of ice, is 0.9. Okay, so that's what it says over here, that if the SG of ice is 0.9, what percentage of volume of iceberg will remain submerged in the ocean? And the answer is 90%. But again, guys, if at all, let's say ocean water is denser than regular water. Let's say the ocean water has a density of 1100 kg per meter cube, and ice has a density of 900 kg per meter cube. Okay. Now, if they ask you what fraction is submerged in water, then your answer will be 9 by 11. Okay. And what will be outside? What fraction of iceberg would be outside? It will be 2 by 11. Okay, because 1 minus 9 by 11 is 2 by 11. Okay. Let's talk about the next topic, which is apparent weight. So let's talk about apparent weight. Now let me remind you how we humans understand weight. When we stand on a weighing machine and we look at those numbers, we understand weight. Oh, that's my weight. Like for example, if I stand on a weighing machine, it'll read 80. So my weight is 80 kgs. Actually, that's the normal reaction force which the machine is recording. I mean, it's quite obvious. If I take a bag full of books, hold it in my hand, then I stand on the weighing machine, it'll add my weight and the book's weight and then give me the reading. So basically, the machine tells us the normal reaction, right? Something similar happens in case of a spring balance too. If I hang a bunch of weight on a spring balance, the spring balance is going to record the tension in it, and that tension is going to be recorded as its weight. Okay. So the way we observe weight and the way weight is actually applied are two different things. Weight is actually applied by the Earth's pull on the object. If Earth is pulling me downwards with a force of 800 Newton, then my weight is 80 kgs, because 80 times G. But if I stand on a weighing machine and the weighing machine records 800 Newton, then it is the normal reaction that is being recorded and is being told to me as if it is weight. It just so happens that the normal reaction and my weight are actually equal. But what if they are not? What if I put this object, which has a weight of mg, in water or any fluid? Then this will start experiencing a buoyant force in the upward direction. And then this string will observe a different tension compared to this situation. In this situation, the string will experience a tension force equal to the weight itself, right? But in this case, the string will now experience a different force than mg. What will it experience? It will actually experience the apparent weight, which is mg minus the buoyant force. Let me draw the buoyant force here. So the apparent weight decreases when an object is submerged in water. Have you played this video game called Uncharted 4? It's a beautiful video game. I mean, if you are a gamer like me. So I'm not going to give you any spoilers, but in that game, there is a scene in which our main protagonist has to help somebody pull themselves out of a very large weight which is lying on them. And do you know how he does that? He does that by flooding the entire place with water. How does that help him? Flooding the entire place with water causes the heavy weight on this person to experience a buoyant force, and that reduces its apparent weight. So it's easy to lift something in water, and you must have experienced this when you are in a swimming pool. It's relatively easy to lift an object out of the swimming pool, but once it's outside the swimming pool, once it's in the air, it feels heavier because now the buoyant force is absent. All right. So what is the apparent weight? The apparent weight of an object reduces when it is immersed in water by an amount equal to the weight of the displaced water. And you already know what is the weight of the displaced water. It is the buoyant force. For example, if the reading of weight of an object reduces from 5 kg to 3 kg, that must mean that it has displaced a water equal to 2 kg mass. All right. It implies that it has caused an upthrust of 2 kg water, and hence it has displaced 2 liters of water. In case you don't know this, the mass of 1 liter of water is 1 kg. So if it is displacing 2 kg of water, then it must have a volume of 2 liters. So with the help of apparent weight or with the help of buoyant force, you can judge what's the volume of the object. So if it is displacing 2 liters of water, then it must mean that the volume that it is displacing is also 2 liters. So its own volume can be 2 liters. So this is the formula that I would like you guys to remember. Apparent weight in case of full submersion is mg 1 minus sigma by rho. Okay. Sigma is the density of the fluid. Rho is the density of the object itself. Now this 1 minus sigma by rho times g can be written as g effective. Let me just write it over here. G times 1 minus sigma by rho is g effective. Okay. And JEE loves this kind of thing. They just adore making you use G effective in all sorts of situations. So let's now discuss. There are two objects, metal and plastic. They are made of two different materials. However, both these objects have the same volume. Now, what do you think is going to sink? Metal or plastic? Metal is going to sink, right? What about the plastic? It's very likely that the plastic goes up and begins to float. So, in these two cases, who will have a larger buoyant force? Which one of these objects will have a larger buoyant force? And the most common wrong answer is that plastic will have a larger buoyant force because you believe that plastic should go up. But the real truth is that because their volumes are equal and they're displacing the same amount of volume, they will have identical buoyant force. Metal will sink because its apparent weight is large. Its weight minus the buoyant force is still in the downward direction, which means that apparent weight is greater than 0, and that's why it will sink. But if apparent weight comes to be negative, which happens in the case of plastic, then the plastic piece must start moving up and float. So what I mean to say is that you see that the sigma by rho, if this sigma by rho comes out to be more than 1, which means that sigma is greater than rho. Sigma is the density of the fluid. Rho is the density of the object, which means that if sigma by rho is more than 1, then 1 minus sigma by rho will give you a negative number. And if that gives you a negative number, then the apparent weight becomes negative. And in that case, the object begins to move up. And I am also sure that you must have taken a plastic ball in your bathtub, pushed it down, and then you would have waited for it to bounce up, right? We all play that game. And why is it happening? What is the physics behind it? The physics is very simple. The apparent weight of the plastic ball inside the water is negative. And that's why it is being pushed up. The buoyant force is more than its own weight. And that's why it comes up. But very importantly, guys, you must remember that if metal and plastic, there are these two different materials and they have the same volume, the buoyant force will be equal because the buoyant force depends upon how much volume they are occupying in the fluid. Let's take a look at this question. there is a 10 centimeter side of this cube and it has a mass of 10 kg. He's asking us the tension in the string. So let me draw the free body diagram. Like I always tell my students and to you that the first rule of mechanics is to draw the FBD. The free body diagram, you draw the weight 10g obviously, and there's a tension acting. But what is the buoyant force? Guys, here's how you find the buoyant force. Look at this information. It's 10 centimeters. 10 centimeters has, it's the cube's edge length. So what's the volume displaced? Volume displaced. Volume displaced is going to be 10 centimeter the whole cube. Because that's the volume of a cube, 10 times 10 times 10, side cube. So 10 centimeter times 10 centimeter times 10 centimeter, and that is 1000 centimeter cube. And my dear students, what is the centimeter cube? I have told this to you that 1000 centimeter cube is nothing but 1000 milliliter. A centimeter cube is the same as a milliliter, and 1000 ml is just 1 liter. And what is the weight of 1 liter water? It's 1 kg, which means that there must be a buoyant force upwards. There must be a buoyant force upwards of how much? Of 1 kg weight, means 10 Newton. All right. So there is a 1g of buoyant force acting up. Let's call it FB equals to 1g. There is a 10g of weight acting down, and then there is a tension acting up. So that means T plus 1g should be equal to 10g, and that's why our answer is 9g. So the tension in the string, the answer is 9g. All right. You could have done this very quickly just by knowing that, oh, 1 liter water is being displaced. So 1 kg buoyant force upwards. That's it. 10g minus 1g, 9g. 90 Newton is the answer. Now let's take a look at another question. There is a stone, okay, and this may remind you of some story from Ramayana. Remember floating stones? There's a stone and that's floating. How is it floating exactly? What is the physics of it? How can this stone even float? It's made of a material and it has got a specific gravity of 3.5, which means that its density is 3500 kg per meter cube. It's 3.5 times heavier than water. Still it is floating. How? Let's find out. So it appears to be half submerged in water. So there is the stone, there is the magical stone, and you see that it is floating on water. Or is it magical? Actually, it is not magical. You know that there must be a cavity inside of this stone. There has to be a cavity inside of this stone. How so? Assume that there is a cavity, guys. Assume that there is a massive cavity inside. What is this cavity? This cavity is like a hollow space. There is nothing inside. Nothing inside. We are assuming there's not even air inside. Okay. So what it means is that the weight of this stone is concentrated in this region. In this region. Oh, we're drawing it with brown color because stones are usually brown. This is the region in which the stone has some mass. So if the cavity has a volume of Vc, then V minus Vc is the volume of this shaded region. We multiply that with 3.5 times rho to get the mass of the stone. All right. Now this mass of the stone will have a certain weight. We can multiply this with g to get this weight of the stone. Now this should be equal to the buoyant force which is acting on it. And now how much buoyant force is acting on it? Guys, whatever the total volume is, it appears to be half submerged. Half submerged means what? Means whatever volume it has, the total volume divided by 2, that is the amount of water that it has displaced. Multiply that with rho w, multiply that with g, and you will notice that you get the buoyant force. Rho wg cancel. And what do you get? This 3.5 comes down. 3.5 times 2 is 7. Okay. So this 3.5 comes down, it becomes V by 7. V minus VC is V by 7. So now you do a little bit of arithmetic. VC goes to this side, V by 7 goes to that side. 1 minus 1 by 7 is 6 by 7. So the cavity has a volume of 6 by 7 V. All right, it's 6 by 7, which means that 85.7% of this whole thing is hollow. And that is how you can make stones float on water if they are hollow. All right. So hollow stones, I mean, it's difficult to make a hollow stone, but yeah, if you can make one, you can make it float as well. Let's now take a look at a very good question. We have a cone over here. It's a solid cone. All right. It's a solid cone. Please do not make the mistake of thinking that this is a hollow cone. It's a solid cone. The whole thing is solid. All right. And it is submerged in water. And it is tied to a string. You can see the string, and there's some heavy weight over here, which is pulling the stone down, and the whole cone is perfectly submerged inside water. Atmospheric pressure is P naught, density of this wood is D, and the density of water is rho. This cone is made of solid wood. You are supposed to find out the tension in the string, the force on the slant surface of the cone by the water. So all these things we are supposed to find out. It's been given to us that the height is capital H, and the height of the fluid is capital H. The height of the cone is small h. Okay. So I would like you guys to pause the video at this moment. Think for a second. Perhaps try to solve it. And if you cannot solve it, take a look at the solution. All right. Let's take a look at the solution. So what is happening, guys? We are interested in the FBD. Again, let's draw the FBD. So first rule of mechanics is to draw the FBD. There's a buoyant force acting up. For sure, there's a buoyant force acting up. There's a tension acting down, and there's mg acting down. All right? There's mg acting down. So what is the buoyant force? The buoyant force will be the volume of the cone because it is fully submerged times the density of water times g. Because the buoyant force is equal to the weight of the displaced water. Displaced water means volume of the cone times density of water times g. What is the weight of the cone? Weight of the cone is its own volume times its own density times g. Okay. So we have found out mg. We have found out fb. And we know that the volume of the cone is given by 1 upon 3 pi r square h. The radius of the cone is given to you as r. The height of the cone is given to you as small h. Then that's why this is the volume. And then you take everything and you put it over here, and that's how you get the tension. Which equation are you supposed to apply? Simply T plus mg is equals to fb. That's all. All right, that is it. Wait a second. Wait a second. Tension is acting down, FB is acting up, and W is acting down. Yeah? So there should be T plus mg equals FB. Yeah, that is correct. This should be correct. So it should be FB minus W. Oh, there's a small mistake over here. This is a minus T over here. That equation leads us to this. W minus FB is minus T. Yeah, correct. So W is 1 upon 3 pi r square h, and there's a d minus rho. Perfect. This is fine. But remember, guys, this is minus t. So t comes out to be equal to 1 upon 3 pi r square h g rho minus d. Okay, it's not a d minus rho, it's a rho minus d. Okay. So let's move on to the next part, which is to find out the buoyant force, like not the buoyant force actually, the force due to the pressure on this cone from the top. Okay. So guys, we have understood one very important thing, that the force due to pressure is itself the buoyant force, right? That itself is the buoyant force. We already know the buoyant force, right? We already know it. We have found it here. We have found it here. Where? Here. Volume of the cone times rho g. That's the buoyant force. We already know it. But the interesting part over here is that you see that this is the slant force. It's acting on both these sides. So, if I have a cone and if I push it from here and if I push it from here like this, don't you think that the horizontal components will get cancelled? Like if I try to push something like this and if I try to push something like this, where will it go? It will go down. It will not go right, it will not go left, especially if both the forces are equal in strength and equal in angle, which you will see that on the cone, everywhere these forces will be applied. Okay, these forces will be applied from here, from here, from here, but the horizontal is going to get cancelled. So there's only going to be a vertical downward net force, which is what we are interested in. So this downward net vertical force, which is F2, is what we are interested in. So this downward force, and then there is the upward force. Okay, there's going to be an upward force. What is going to be the upward force? You see that there will be a certain depth up to here, and this depth is going to give us some force from underneath, like that. Okay, and that is what will be that force will be the pressure at this point times this area. All right, the pressure at this point times this area. So let's take a look. So what is the pressure? What is the pressure at the bottommost point? So it is P naught plus rho gh. Okay, guys, you can assume that this string is like almost negligible in length. So that's why we have taken rho g capital H. I mean, this length is like from here to here. It's not the whole length. So this rho g capital H plus P naught, which is the total pressure at the bottom face. Okay, like there is liquid up to a height of capital H on top of it. And then you multiply that with pi r square. Pi r square is this area. Pressure multiplied by area is force, right? That's what we have done over here. So this is the upward force minus F2, which is the downward force. We are interested in this F2, and that should be equal to the total buoyant force. And that's it. You can leave the answer in this manner, that F2 will come out to be this minus this. Okay. Let's take a look at another question. If you want to take a look at this once again, if you want to copy it down, you can pause the video and then do it. And then we can move on to this question. Now this question is very interesting, guys. He's asking how much weight can I put on this block of wood which has a specific gravity of 0.7. So remember one thing, guys, that if there's a specific gravity of 0.7, then 30% of this must be floating outside. Okay, it must be floating outside. So if this cube has a total volume of, let's find out the total volume of this cube. The volume of this cube will be 0.5 whole cube, correct? That will be the total volume of this cube. And I know that 30% of this is still outside. This is SG 0.7, okay? So 30% is 0.3 times 0.5 whole cube. Okay, let me just write this. 30% of volume of the cube is this. Okay. Now this volume can be further pushed down. Okay. So what more weight can be displaced? More weight that can be displaced. More weight of fluid that can be displaced is 0.3 times 0.5 the whole cube multiplied by density of water, which is 1000. Okay. And remember, guys, that the volume is a meter cube. So we don't have any problem with this. And this is the weight that can be supported by this block of wood. So if you put the same amount of weight on top of it, then this part will get submerged and it will support that kind of weight. Okay. So what is 0.5 times 0.5 times 0.5 times 1000? It's 125. 125 times 0.3 is going to be what? I think it's going to be 37.5. 37.5 kg. That much, 37.5 kg of mass can be put. And if he's asking weight, then weight will be just 37.5 times 10. Okay, so your answer becomes 375 Newton. Or if he wants to be more accurate, you can look for the options if he wants you to multiply it with 9.8, which I don't think he will want, but okay. You can multiply it with 9.8 or 10 depending upon the requirement. Okay. Let's take another look at this one more question. Now there is a cube of 400 grams, okay, and it has a edge length of 10 centimeter. So what is its density? I just wonder. By the way, remember guys, these are all JEE questions, okay? This is also a JEE 19 question. This is also a JEE 25 question. So these are all nice JEE questions. You can see that they are not that difficult. I mean, they are pretty doable. So let's find out the density of this cube. The density of this cube comes out to be 400 grams upon 10 centimeter. Now 10 centimeter cube is 1000 centimeter cube. So this is equal to 0.4 gram per cc. So what is its SG? SG? Its SG is going to be 0.4 gram per cc upon 1 gram per cc, which is just 0.4. So if I throw this block inside water, 40%, because 0.4, 40% of it will be underneath. 60% of it will be outside. So our answer is very clear. Our answer is, he's asking how much volume of the cube is outside. Our answer is 60% of its volume, which is equal to what? 1000 cc, and that is what? 600 cc. Oh my God, such a simple question. Easy peasy lemon squeezy. Now I would like to show you guys a question from JEE Advanced. Okay, and then you will wonder that, oh, perhaps JEE Advanced is also not that very difficult. And my dear students, the truth of the matter is that yes, JEE Advanced is a competition which can be put in your grasp if you are slightly bit dedicated. The problem with most students is that they leave the journey halfway. The biggest factor that will make you win is not your intelligence. It's your consistency and the strength of your heart. Okay, there should be fire in your heart, guys. You will see how doable this question is. If this question comes in your exam, you should look at it and you should feel, I am getting selected. So let's read. A solid sphere of radius r and density rho is attached to one end of a massless spring of force constant k. And the other end of the spring is connected to another solid sphere of radius r and density 3 rho. So guys, what have I done? I have made a sphere of density rho and radius r. I have attached it to a spring. I have done exactly what this statement is asking me to do. And then I have taken another sphere of radius r and density 3 rho and I have attached it to the spring. Now this complete arrangement is placed in a liquid of density 2 rho and is allowed to reach equilibrium. So what I have done is that I have filled the whole thing with the fluid of density 2 rho. Okay. And now I have allowed it to reach equilibrium. So what are the correct statements? So I am supposed to analyze this situation and I am supposed to think what's going to happen in this case. So guys, what is the best way to go? The best way to go is that we find out the FBD of both these. All right. So let's draw the FBD of the smaller block. Because you see, I've taken the weight of this as rho Vg. The smaller one has a density rho. It has a volume V. I mean, you can put it as 4 by 3 pi r cube. The volume of sphere is 4 by 3 pi r cube. That's why you can put it as that. But for now, I'm putting it as V. So rho Vg is the weight downwards. But what is the buoyant force? Buoyant force is 2 rho Vg. I'm assuming complete submersion. If that's completely submerged, then there's an upward force of this minus this. 2 rho Vg minus rho Vg, which is how much? Simply rho Vg. And if I'm assuming that this is in equilibrium, then 2 rho Vg should be equal to rho Vg plus Kx. Now what is this Kx? Kx is the spring force, all right? Now if I calculate x from this equation, I just simply get 2 rho Vg minus rho Vg, which is rho Vg, divide this by K, and that gives me the value of extension in the spring. Okay, if you look at the options, yes, there is one option like that. 4 pi r cube rho g upon 3k. 4 pi r cube rho g upon 3k. Okay, so this is correct. But guys, remember, we have assumed complete submersion. Okay, it's not half submersion, we have assumed complete submersion. So our like, you should not be readily marking option A at this point, because we have made an assumption. Now you see, if our assumption is correct, then this same force Kx will also be involved in keeping the larger, like the heavier sphere at equilibrium. Let's draw the FBD of the heavier sphere. Now the heavier sphere is over here and it is experiencing a Kx in the upward direction. See, the spring force is kind of like tension only, okay? Like if it is pulling this block downwards, just like how tension would, it will be pulling this block, this sphere, upwards, and those forces will be the same in magnitude. So we have assumed the same Kx force acting over here. Okay, so the buoyant force would be the identical for both of them because they have the same volumes. So 2 rho Vg up, and Kx is what? We have found out Kx, guys. Kx is coming from here. Kx is actually rho Vg. Kx is rho Vg. So I have put Kx over here, I have put Fb, and then downwards is 3 rho Vg. If you calculate this whole thing, then it comes out to be 0, which means that our assumption of full immersion is correct. It would have been wrong if this was not at equilibrium. Okay, then we would have figured out another way to solve this problem, which means that yes, the light sphere is completely submerged and the net elongation is given by option A. So I hope you guys enjoyed doing this JEE advanced problem, and this marks the end of fluid statics. From the next lecture, we will be beginning with fluid dynamics, and I wish you all the best, guys. Stay tuned to the channel and I will keep uploading such amazing videos for you guys in the future. Till then, stay physics rich.